Hello friends, this video on alcohol, phenol and ethers part 28 is brought to you by examfear.com. No more fear from exam. Let's talk about the chemical reaction of ethers. Ethers are generally inert, but they react in drastic conditions, right? So in the ether we'll see the cleavage of CO bond. If you see ether, we have something RCH2O and something like this, right? So CO bond cleavage you will see. So in CO bond cleavage, we'll see the hydrolysis, halogen acid reaction, we'll see PCl5 reaction. We'll also see the reactions of oxygens. We'll see electrophilic substitution reaction. In that case, we'll see halogenation, Friedelcrafts reaction, and nitration. So we'll see these kind of reactions for ether. First, we'll see hydrolysis. So let's see this reaction here. So this is a CO bond cleavage. It's called hydrolysis. You have ether, and you take dilute sulfuric acid, have some water, some pressure, some heat, you get alcohol. I think you have seen this reaction. So we have, this is SN2 reaction, by the way. This is an ROR, you have some water, sulfuric acid, you get ROH. 2 ROH actually. Want to see the mechanism? So I have R, I have H plus here, so which has electrons here, oxygen has electrons here, so let's write this H plus here. Since oxygen is giving electron, oxygen will give positive charge, right? And this will be H and this will be R. Now since oxygen has positive charge, one has to leave, so R will leave here, correct? So R will leave in this fashion with a positive charge here, this bond will break. Right, this gets negative, this gets positive, positive, negative neutralized in oxygen, and R gets positive charge. So this is ROH plus R plus. So R plus will somehow get OH minus from water, right? It will react and it will form 2 ROH. Pretty easy reaction. Let's see the halogen acid reaction. So if I have R1OR2, when I react with HX, right, some halogen acid, what you get is you get R1X plus R2X. You get 2 alkyl halides. Correct? So the reaction goes like this. First you get 1 alkyl halide and 1 alcohol, and then the next alcohol, the alcohol reacts again with HX to forms alkyl halide. So end of the day you get 2 alkyl halides. Correct. So maybe I can draw in this fashion. So this one will give you R1X plus R2OH, let's suppose. And then again when you add HX, you end of the day you get this. Correct. So, or if you see this compound, this is my, let's suppose OR. You add with HX, you get OH. This is phenol and this is very stable, right? And you get RX. So order of reactivity of halogen, again same thing will repeat, HI, HBr, HCl. This is most reactive. So this can be SN1 or SN2 reaction based on various conditions, right? It can be SN1 or SN2 reaction. So let's see the reaction mechanism here. So let's suppose I have CH3O C2H5 and let's react HI, H plus I minus. These are all electrons, lone pair. So this lone pair will attract this hydrogen here. So what you get is CH3, since oxygen is giving electron, will get a positive charge, H and C2H5 plus I minus. I minus is a very good nucleophile. Will attack this carbon and this bond will break, right? So overall it will become neutral, so it will become CH3I plus C2H5 OH. That is the first step, right? R1X plus R2OH. Now the C2H5OH, if you have more HI, then you know what will happen. Everything will get, again same thing will happen, right? This will attack this H, right? And OH2 will go now, so it will become C2H5 OHH, oxygen will be positive charge, and then I minus will come, it will take this position and OH2 will go off, right? It will become C2H5I. So end of the day you will get CH3I and C2H5I as the product. So please note here that I minus can attack CH3 and C2H5, any of these, but the rule says that I minus will attack the less substituent carbon. So here it is C2H5, CH3, right? So it attack this CH3, the lower carbon. That is the rule. But there is an exception to this rule, and this is only for the tertiary one. So if you see this exception here, so in this, if I attack HI, this is a lone pair here, so attacks this H plus, correct? So what you get is this O with a positive charge, and there is a H and there is a C. Now you see this is, now there is a rearrangement that happen. The rearrangement will happen and positive charge will go here, right? How this bond will break in this fashion. With this you get stable carbocation. You see here with this I get this stable carbocation and COH, correct? This is, you can add H3 here. So if you see here, what I'm getting here is stable carbocation, and on this my I minus will attack, correct? So the output here I'll get is this guy I plus CH3OH. You can add CH3 here. So if you see, there's a exception to this rule now, right? Because normally we have seen that I comes with the smaller hydrocarbon, but in this is the exception only for the tertiary one, because here to form this stable carbocation there's a rearrangement that happens. This rearrangement happens and this causes the exception, correct? We'll take one more strange scenario. So I have this phenol, this O, and then we have CH3. Again, let me react with HI. Now same thing will happen. This will attack this H plus. So what you get here is this compound. Let me draw it here. O, then H and O will get a positive charge, and CH3. Now the question is which one will leave, whether this bond will break or this bond will break, correct? Now if you see this, let me change the color. I have OCH3 bond, that is a weak bond, and this O and this carbon bond is a strong bond. Why? This has partial double bond character, right? It has partial double bond character because of the resonance, so it has a strong bond, is a weak bond. So which one will break? Obviously this will break. This will break. So what you get here is OH plus CH3 plus. And on this my I minus will attack and it will form CH3I, and this is my phenol. Correct? So you understood why this bond break, because this is weak, this is strong. So O plus is a very stable thing. Oxygen will never want to have positive charge. Oxygen is the electronegative element, so it will give the, and it will ask one of the bond to break. So this bond will break because it's a weaker bond. Now we'll see the reaction with PCl5. So here both the CO bond breaks actually. So I have, and this is SN2. So I have ROR. You react with PCl5. What you get is 2RCl and some PuCl3. For example, if you have C2H5, OC2H5, then you react with PCl5. What you get is 2C2H5, Cl and PuCl3. We'll see the mechanism now. So let's see the mechanism. Right? So I have ROR with electrons here. I have PCl5. Cl, Cl, Cl and Cl. Correct. This phosphorus again is electron deficient. This oxygen will give its electron to phosphorus, and phosphorus won't be able to hold much, so when chlorine will come out. Since oxygen is giving electron, so oxygen will get a positive charge. So with this, what you get is R with a O with a positive charge, and P with 4 chlorine now. And once chlorine came out. Till now it is clear. See, this is a lone pair of electron. It will give it to phosphorus, which is in need of electron. One chlorine comes out, so the phosphorus oxygen gets a positive charge. Now this oxygen gets a positive charge is not good. This R will say, okay, I will go off with a positive charge, and this will give a negative charge to this oxygen, so negative and positive will get balanced, right? So this will get me R plus, and this R plus will combine with Cl minus. So you'll get RCl here first, and what you get here is RO P Cl 4 times. Correct? This is what you get. And this is unstable actually, this is unstable. So what will happen is this oxygen, right, will again attract electron towards itself. This will go in this fashion and this will go in this fashion. Yeah, this will happen. Correct. So now what will happen is with this I get R plus out. Again, one more R plus out. So this RCl is done. We are done with RCl. What here you get is R plus, and this Cl minus will again combine with this R plus here, right? This will combine here with this R plus. You get RCl actually, R plus Cl minus, right? And what you are left with here is P. It will be double bond with O, and Cl. There will be 3 Cl here. POCl3. Correct? So you get 2 RCl, in fact this is RCl, 2 RCl and 1 POCl3. Pretty good. Oh. So let me repeat this reaction. You have ROR, this oxygen has lone pair. This lone pair goes to this phosphorus, which is in need of electron. Bond forms, oxygen gives electrons, so gets a positive charge here, right? And you have this chlorine comes out. Now this oxygen got a positive charge, not good. So this R will come out, in this electron will flow in this direction, R will come out. R and Cl minus, R plus Cl minus will form RCl. Now this is also unstable now. So this R also wants to come out, right? It will get electron, oxygen is more electronegative, it will try to attract electron towards itself. It gets, and this oxygen will go to phosphorus, is in need of electron. This chlorine comes out. So this chlorine and R plus which came out forms again RCl, and what you are left is POCl3. Correct? Now we'll see reaction with oxygen. So I have ROR, and it reacts with oxygen, it forms R, this O and this R. This is called peroxide. Right? So it is in the presence of UV rays and no water, no moisture also. No moisture. Correct. For example, if you want, you can take this C2H5O, C2H5, you react with the oxygen in the presence of UV rays without any water, you get this compound. This is my diethyl ether peroxide. Correct. Let's see this electrophilic substitution reaction. So just as OH is electron donating group, similarly ether, that is OR, is also electron donating group, right? They also donates electron and they activate the benzene ring for electrophilic substitution reaction. So if you see you draw the structures, the resonance structure, you will get something like this. Correct? If you draw more, this electron will move in this direction, you will get something like this. If you draw more, you will get something like this. Correct? So if you see, it is all negative charge. Here, here, here. So just as phenol, if you see, my ether group also activates the benzene ring towards electrophilic substitution reaction. So we'll see the halogenation reaction. So for halogenation, we can have a normal ether, aliphatic ether, for example this. If you add chlorine, this is carbon here, yeah. If you add chlorine, it will keep replacing one hydrogen each one time. Any hydrogen, maybe this hydrogen, there are so many hydrogens. Let me draw the hydrogens first. Yeah. This hydrogen, it will keep replacing hydrogen in dark. Right? And end of the day, what you will get is C2Cl5 2O. This is what you will get. This is perchlorodiethyl ether. One by one, it will replace this hydrogen with chlorine. Let's see one aromatic thing. So here, similar to phenol, I have OCH3 here. If I just add bromine in ethanoic acid, what you will get is, here also you will get ortho and para position. So ortho is the major one. I'll not go for the reaction mechanism. We have discussed a lot for this in phenol. Yeah, and this reaction is again electrophilic substitution reaction, and this reaction is faster than benzene. Why? Because if you see, you take a normal benzene, you add a bromine, there is no reaction. There is no reaction. But for the reaction to happen, generally we add bromine and we add something called FeBr3 and we give some heat. Right? With that we see a bromination happen. But here we see directly only you are getting the bromination reaction. So this is pretty fast. So as compared to benzene. Why? Because OCH3 is it activates the ring for electrophilic separation reaction. Next, the Friedelcrafts reaction. This also we have seen earlier for phenol. So I'll not go for the reaction mechanism. Similar to this, Friedelcrafts normal reaction and Friedelcrafts acylation reaction. Yeah. So if I add CH3Cl in presence of AlCl3, right, and CS2, what you get here is, so this hydrogen is replaced with CH3, or you also have one ortho product, correct? And this is my major. So this is called 4-methoxytoluene, correct? Similarly, I have this reaction where I have this OCH3 here, and I can use CH3 COCl here. This is acylation in AlCl3 CS2. So here what happens is, instead of CH3, what we add here is COCH3, and here also we'll add ortho position, yeah, COCH3, and this again is a major product. Same reaction mechanism, not a big thing, actually pretty easy, right? This becomes CH3 plus, attacks and kicks out this hydrogen. So we have seen this reaction mechanism a lot. So if you have issues, you can just watch my previous videos where we explained the Friedelcrafts reaction mechanism. You can look into those mechanisms. Similarly, we also have nitration. It's exactly similar to phenol. We have nitration here. We have OCH3. So when you use HNO3, you need some sulfuric acid because you need to form NO2 plus ions. Right? So what you get is two products. One is ortho and one is para. Correct? And in this case, this is my major, nitroanisole. Same electrophilic separation reaction, right? Same thing, NO2 plus we have. So HNO3 and H plus will form NO2 plus, and NO2 plus will, again, if you want, I can draw this one at least for you guys to just show it is same, right? So I have NO2 plus with a positive charge. This bond will break and it will attack this guy. So it will break into negative. This will break into this direction, negative and positive. So on the negative side, you attach this NO2. This gets a positive charge here, right? The aromaticity breaks, correct? So to bring back aromaticity, this hydrogen goes off in this fashion, right? And this you get aromaticity back, correct? This is the reaction mechanism. Pretty easy. Let's take. Thank you. Visit our website examfear.com to watch more and more quality educational videos. You can also attempt free online tests that are there in our website. You can also get access to tons of free study materials, and you can also find free tutors and mentors in this website. Thanks a lot for watching.